All right, also, what we're doing today are this least squares regression line. And so we've done this in your math classes. And what we've always called this least squares regression line is your best fit line. So what you'll see in stats is this least square regression line. We find this using linear regression. It is a best fit line, and it's often abbreviated LSRL. And that's this line. So I have highlighted up here 3 AP Classroom videos that I think are really good because we're going to talk about residuals and residual plots, and those are a new thing in stats. You've never done these in your other math classes, so it might be good to go back and review these. In fact, I'll pull these daily video worksheets and put those in your notes packet. So least squares or linear regression. So we're going to make a best fit line on our scatter plot to be able to better interpret the relationship between the two variables. And here's really what we're doing: make predictions about our response variable. Okay, so I have this graph right here, and I have a scatter plot, and we have this best fit line, and we can draw a best fit line, but when the calculator or computer draws a best fit line, then we know that that line is accurate, right? So it takes all of this data through this process that I'm going to show you today and comes up with literally the best fit line, okay? So a regression line, that's what we have right here. A regression line is a line that models how the response variable y is going to change based on x. So this all goes back to this f of x again, right? How is y going to change when we plug in different values of x? So what we know is that the regression line follows the same format as a normal line. So we would have y equals ax plus b. Now, you see a change. So this is, I'm using the variable a instead of m for slope because this is what your calculator uses. All right. Now, in stats, we also see this as y equals a plus bx. And that can be a little confusing. In fact, let me just show you this on the calculator real quick so you can see what I'm talking about. If I go in here and I do a linear regression, I have ax plus b, number 4 right here. But if I go down to number 8, I see a plus bx. Now, the difference between these two is just that in stats, we tend to go in decreasing order. So in stats, you're going to see it written as a plus bx, and that's not b like the intercept. It's just saying that the value that's connected to your x term is your slope. So up here, we're using a, down here, we're using b, but it's still the slope. It's the same thing with our intercept. A and b, you just have to look at what's connected to your x. What is that coefficient that's on your x? Well, the other part about a regression line is that the regression line, while it follows this format, we don't actually have an exact y value. So what happens is, when we have this best fit line and we're plugging in a number along this best fit line, what we're saying is, if I plug in some value, it would hit the line. Well, we don't know that. We don't know that it's going to be on the line. It could be above the line or it could be below the line, right? All of these data points are above or below this line. So we don't write this as y equals. We put this little hat on top of the y. And so what this looks like, it looks like what we see right here, y with this hat on it. In fact, this is called y hat. That's how we pronounce that. That's y hat. And what this is it is a predicted value of y. It is not an exact value of y. It's just a predicted value of y. And that's really what this says. This says, what is the difference between y and y hat? So y is the actual value, and because we're using a best fit line or a linear regression line, y hat is the predicted value. So we're going to assume that the predicted value is super close, but that's what it is. It's just predicted. Okay. So again, what you're going to see from your AP formula sheet for your least square regression line is it's going to look like this. Y hat equals a plus bx. And then y hat right here is our predicted value. And then our explanatory variable, remember that's our x variable that goes on the x-axis. The slope in this term is b, and I'm going to say that this is the coefficient of x. And then the y-intercept on this case is going to be my a value. Now, another way that I can write this is y hat equals a plus bx. Now, this is different. This value is my intercept, and this value here is my slope. Okay? All right, so a couple words. So slope is the same concept that we've dealt with since 8th grade. So slope is just the rate of change in the linear regression line. So the slope of the regression line is important in the sense it gives us the change in y with respect to the change in x. So this is still a rate of change. And it's still change in y over change in x. Okay? Now, this part is a little bit different, the intercept. The intercept is statistically meaningful only when x can take values close to 0. So there are times where, from a line standpoint, we're going to have an intercept, but it might not make any sense. So let me give you an example of something. Let's just say, I don't know, I'm trying to make something up right now. We have cost up here, so cost of a house, and let's do square footage here. So square feet of a house. So if I think about this, if I have a 10,000 square foot house, my price is going to be significantly high, right? If I have a 5,000 square foot house, my price is going to come down a little bit. And if I have a 3,000 square foot house, my price is going to come down a little bit. And so what happens to this line is we have a line that's going to look something like this, right? Now, what this means is I have this y-intercept that's a negative y value. So when x equals 0, so my f of 0 function here is going to be negative. Let's just say it doesn't really matter, negative 500, right? So what this is saying is if you have a house that has 0 square feet, it's going to cost you money. It's minus 500. And so this just doesn't make sense. So there's no logic in this example because we're not going to have a negative value here. You know, if you have a house that's 0 square feet, it's possible for that value to be 0, but I'm not going to have a negative value. Okay? So be careful when it's talking about the intercept because the intercept might not always apply. Okay? All right, let's see where we're at. Okay, so we're going to practice this a little bit on the calculator just so we can kind of see how everything comes together. And so from your calculator, I think I already put this data in. Let me look. Yeah, I did. Okay, so from your calculator, what we want to do is we want to put the data in. So here's the question. It says, can you predict the price of a used Ford F-150 Super Crew truck if we know how many miles it has on the odometer? So these are data points. So they went out and they said, okay, if you've got 70,000 miles, this guy sold it for $21,994. If you've got 129,000 miles on it, it's sold for $9,500, and so on. Okay, so step one here is we want to create the scatter plot. So if I have the scatter plot, I'm going to put my miles driven in my x variable, which is my L1, and I'm going to put my price in my L2. So go ahead and pause the video and populate that with L1. So miles driven is L1 and price is L2. And then this continues into this next row. So you're going to have more miles here, L1, and more price. Okay? All right, so now that you have that in there, we're going to check and make sure our stat plot's on, and it is. And I'm going to go zoom, zoom stat. I want to see all the data, and that's the data that I have. Okay? Now, I give you the graph right here, but we're going to talk through this on your calculator because we're going to run some results. So if you didn't actually type this in your calculator, you need to pause the video and go do that. All right, so now we want to create our least square regression line. And so to do that, we're going to go back to stat, and we're going to go over to calc, and we're going to go down to linreg. Now, It doesn't matter which one of these you pick. In fact, I would tell you to do both of them just so that you see you get the same answer. So I'm going to go down here to the stats one, and I'm going to run this, and it says list X list is in L1, my Y list is in L2, and then I'm going to stop here at store regression equation. That's what this means, store regression equation. So if I store this in my calculator, then it'll graph it on my graph. So to do that, you're just going to put the variable in where you want to store it. So if you go to vars, you can go to yvars, and you can pick that, or you can do alpha trace, and I can pick L1. So I'm saving this graph here as Y1. Let me write this down just so you have it. If you want to store your regression equation, that's what this stands for, regression equation, then you're going to hit alpha. There's more than one way to get your variables in there, but if you hit alpha trace, so right here, alpha trace, then you get the variables that come up, and you would pick the one that you want. So I picked Y1, and then I run this and I calculate it. Okay, so if you're not seeing R squared and R on your calculator, then go back and watch my video on lesson 2B, and you need to make sure that you have your stats option on your calculator, or these aren't going to show up. Anytime you do a reset on your calculator, so if you're in physics or something and they tell you that you need to reset your calculator, these two variables might go away. Your R and your R squared variables might go away. And so you need to make sure that you go back and add those in by going back to mode, and then you go down to stat diagnostics and turn that back on. Okay, all right, so let me go back and rerun this. I saved it already, so we're good. All right, so here's what I have. So I have this equation, and the equation's going to tell me y hat equals 38,257.14, and this is money, so I went ahead and rounded it to 2 decimal places, minus 0.163x. Now, the second time I ran this, I did ax plus b, but really all I care about is what term is going to be my coefficient. So I wrote this in the stat term of a plus bx. Okay, now when I do this, this is now my least square regression line. But what we're going to do is we're going to change two things, and I've got it for you right here. But we're going to change this y hat to what we're actually looking for. So my y variable is my y-axis. So I'm going to change this to price. That's what I'm searching for, and I'm going to put my hat over price. So this is my predicted price, 38,257 minus 0.163, and I'm going to replace this x with what I'm finding on my x-axis, and this is going to be miles driven. So when you write these down, you're not going to write y and x. You're going to actually put in your y-axis label and your x-axis label. Okay, so a couple things that we can do here. So what is the price when 53,000 miles are driven? So if I go in here and I put my 53,000 into my equation, I'm going to get an answer. So let's look at what that is. So 38,257 minus 0.163 times 53,000. Okay, so what this tells me when I plug this in is that it is the price, predicted price, remember that's what that hat means, predicted price is going to be $29,618. And if I look over here and I come out to 53,000 miles, so it's going to be in here somewhere, and I come up to my line, yeah, that's probably about true. Now, what we can do is we can pull this directly from the calculator, though. So if you remember, we stored our regression equation. So when we store our regression equation, and I stored it in Y1, it stored the whole equation without any rounding. And so now when I graph my line, I see my scatter plot, but I also see my least squares regression line, my best fit line. So if I want to know what's happening at 53,000 miles, I'm going to go in here and I'm going to do second trace. So I'm going to hit calc, so second trace, which is calc. And I want to know the value So when I hit value on my calculator, it says, okay, the value when x equals, well, when x equals what? When x equals 53,000. And it gives me the answer right here. It's kind of small, but what it says is it is 29,622.45. Now, super close to this value, right? These two values are really close. Now, the only reason there's a difference is because the calculated value from the least square regression line is not rounded, and the value that I used when I plugged into the calculator, that is a rounded value. Okay, so you can find these both ways. It's going to ask you to write the equations, so you need to make sure that you write it this way, where you have the price and you would have miles driven. So you're replacing your y hat and your x variable with those. Okay. So what we just did is we looked at this best fit line and we predicted, remember that's the goal of a regression line, is we predicted what our value would be. So if we drive 53,000 miles, it's going to be about $29.6 thousand. Okay. Now, we can also extrapolate. So we can take this line that we had and we can say, okay, we're going to keep going with this line. And so that gives us data that's around our line, like before or after our line. What this says right here is use caution when doing that. So if we're giving a prediction outside the interval of your x values, be careful. So it doesn't, if we only know in this is true data up here. This is true data. We know that this values are real data. If I want to know what's happening out here at 160,000 miles, I don't have a data point out there. I can assume, I can extrapolate this line and it's going to encompass that point, but that's not always true. So what it says here is correlation does not imply causation. For example, there was a study done that shows a strong positive linear relationship between ice cream sales and homicides in New York. Does this mean if we stop selling ice cream, we will have no more homicides? Again, we talked about this in section 2B. It's the same thing. Causation does not apply, correlation does not apply causation, right? And the other word that we use with that causation is association. So let's look at how extrapolation can be a bad thing. So if I go back to my graph right here, and this time we want to know what is the price of the car when we drive 300,000 miles. So I'm going to do it on my calculator. So I'm going to go back to second trace, and I want to know the value when we're at $300,000. And this tells me that I have an error on this. Hold on, I can actually do this without the error. Here's what I'm going to do. I'm going to go back to my window, and I'm going to make my window for my x value super big. Okay. All right, so that's the same data with a different scale. That's why Zoom Stat is so great, because it scales it for you. But here I made my scale bigger. And now what happens is I want to go in and I want to find a value at 300,000. And it tells me that the value is negative 10,618.43. So negative 10,618.43. Now we would have gotten the same value if we would have done this. It would have been slightly different because remember this calculator value is not my rounded value. So here's an example of how extrapolation is not going to work. So what this is saying, this says if you drive 300,000 miles, then the cost is negative 10,618.43. So this is saying somebody's going to pay you to take the car, and that's not going to happen, right? So just like our other example a minute ago with house price and square footage, this is kind of the same thing, all right? You have to be careful when you extrapolate because the data doesn't always make sense. That's the purpose of this section right here, okay? All right, okay, so let's go back to our line right here. So what happens is, as I look at this best fit line, I see that this first point hits pretty straight on. This point is below. and this point is above, and this point is more above, and this point is a little bit above, and this point is way below. Well, this difference that I have from the point to the least square regression line is called a residual. And so what this says is, in most cases, no line will pass exactly through all points. Here, I'm going to make this so that we can see this better. Okay, so here's my graph that I was just working on. And it says, in most cases, no line will pass through exactly all points. You have to have a perfect linear slope for that to happen, like go through all points. This means that even if we use our least square regression to make predictions about our dependent variable, there is going to be error from the actual y value. So we said this is the line, but here we're under the line. We said this is the line, but here we're above the line. That's all this is saying. Because we use the line to predict y from x, the prediction errors that we make in y is the vertical distance or the vertical direction in the scatter plot. So we're going above or below that, okay? So let's see, what was I going to say there? Vertical distance between observed value. So, a residual. A residual is the vertical distance. So this would be the residual. The residual is the vertical distance between our line and our actual value. Okay, so here we have this. This is the same graph. This is just giving it to you again. And like I showed, we've got these different residuals right here. So we can take these residuals and we can plot them on a residual plot. So this is a residual plot. And what happens is, it's almost like this best fit line gets turned sideways, and then the distance above and below is plotted here. So we see this point, which is our first big point, is below the line. It's going to correspond to this point below the line. We have these two high points right here. They're going to be these two high points above my best fit line. And so what we see is how far below or above the line we are on this. Now, a good regression line makes vertical deviations from the point from the line as small as possible. So for us to have a perfect line, every point would be on my line right here. That means every point would hit, but that's not true. That's not what's going to happen. So what we do is we calculate a residual by getting the actual value, so the actual value that I have right here, and I subtract the predicted value. So I have this point right here, which would be my actual value, and I have this point that would be on my least square line, my regression line, and that would be my predicted value. So what we have is residual equals the actual minus the predicted. And so we can also write this as the actual minus the predicted. So if we know the actual value, that's our y value, and we minus the predicted, and this gives us our residual. So I remember this like RAP, residual equals actual minus predicted. Okay. If the residual is positive, the observed line lies above our least squares regression line. So when that happens, when it's above, that means that our line is an underestimate. Now this makes sense. This is what we thought we were going to get. We thought we were going to get, what, 43,000, but we only got 34,000. So the predicted is an underestimate of what we really had. All right, if the residual's negative, so the residual falls below my line, then the point lies below. That means it's negative, and the model is an overestimate. So again, if this was the point that I'm looking at, this would be my y point. This point on the graph with my vertical line would be my y hat. That would be my predicted value. So this value, my predicted value, is an overestimate of what I actually got. Okay? So if we look at this, it says find and interpret the residual for a truck that has 70,583 miles and a price of $21,994. So this value right here, this is my actual. This value here is my actual. So what I want to do is I want to plug this into my equation. And so actually, I'm not going to plug it into my equation. I'm going to plug it right in here because it makes it goes faster. So here's my graph. Nothing's changed except for my scale looks funky, but it doesn't matter. And I'm going to second trace. I want to find the value. And this time, the value is going to be at 70,583. That's my miles. My miles are my x-axis. And if you forget, just go back to your graph, right? Your miles are your x-axis. And that tells me that that my predicted, so my y hat value is 26,757.86. Okay, so my residual is my actual minus my predicted. So my actual was 21,994. And my predicted was 26,757.86. So my residual right here is going to be the difference of those two. So negative 4763.86. So that's my find. Now I have to do my interpret. So my interpret would be the truck sold for $4,763.86 less than, that's my keyword right there, less than the value predicted by the least squares regression line. Okay, so negative means it's going to be less than the predicted value. Okay. So prediction lines. We're still talking about prediction lines here. So what we have, it says the strength of the line depends on how close the data points are to the regression line. Well, that makes sense, right? So the strength of this prediction line, we want the values to be as close as possible. So the mathematical approach to describing this is called the coefficient of determination. So we need to create probably a chart in the classroom. So the other day we did the R value, and we said that the R value was the coefficient, coefficient or constant of correlation. Coefficient of correlation. Okay, well now we have the coefficient of determination, and this is R squared. This R for coefficient of correlation and this R squared for determination are the same R. So this is the same R. So coefficient of determination measures the percent reduction in the sum of squared residuals. So here's why this is important. If I go back to my residual plot, these are all positive values and these are all negative values. And so they're different values, but technically, if I look at this one's positive and this one's negative and they cancel each other out, then that would tell us we have this perfect line, and that's not the case, right? So because I have positive values here and I have negative values, it's not going to be an accurate reflection of that because some are positive, some are negative, and your end result might be 0. So what we do is we take this correlation coefficient, the value that we calculated the other day, and we square that value. So in our last example, so in our truck example, we're going to go back and we're going to rerun our linear regression. So we haven't changed any data. I'm going to go back to stat, calc, go down and run our linreg. And again, it doesn't matter if you use 4 or 8. It doesn't matter. When I run this, I have this data. I have an R value. My R value is negative 0.8150. So my R value is negative 0.8150. So let's talk about what this means. So again, what this means, this is what we did yesterday. So what this means is we have a negative linear relationship, and this is fairly strong. So remember, for it to be perfect, this would be -1. For it to be weak, it would be minus 0.01. So 0.5 would be right in the middle. So this is pretty close to 1. And if you look at our line, hold on, let me get that back into what I like to look at. There's our line. So if I look at our line, I hit a lot of data, right? I've got some data that's above and below, but that is a pretty fairly strong linear relationship that we have. Okay, so now if I go back here and get this data again, I have this R value. Now, what we said is that the correlation coefficient squared is my coefficient of determination. So here's what I'm going to do. I'm going to take this R value that I have, and I'm going to square my R value. So if I take negative 0.8150 and I square that value, let me just do that real quick. Oh, 8150 squared. Oh, and I don't have a negative there, but it doesn't matter because you're squaring it, so it's going to go away. So what I get here is 0.6642. My R squared value is 0.6642. So if I go back and look at my data, I get my R squared value from my calculator. It tells me that it's 0.6642. That's where this number comes from, 0.6642. So what does that mean? That means that this coefficient of determination, which is the strength of my least squares regression line, is 66.42%. So again, the coefficient of determination measures the percent reduction in the sum of the squared residuals. So if I look at my line, I have to square that value because this time I'm really looking at, it's almost like I'm taking the absolute value because I don't want this number to be negative. So I get a positive number, but as I do this, I'm actually creating an area. So I create an area, that's why I'm squaring it, of all of those values that are underneath the line. So if I took this and looked at this in terms of an area and created boxes here to give you area underneath the line, that's what we've done when we've done this. Okay, so whenever you use your regression line for prediction, also include as a measure of how successful the regression is in explaining the response. So if we think about this, we would say that our prediction, that the success of this is 66.42%. And that's what this would be right here, 66% of the variation in truck price. So if we took this and put this as part of our interpretation, 66% of the variation in the truck price can be explained by the linear relationship it has with the odometer mileage. So 66% of the variation is accounted for in our least square reduction, in our least square line. Okay, so this gave you the residual plot. I'm going to show you now how to create a residual plot, and we do that on the calculator. It's super easy. So what happens on our calculator is we have, when you run the regression, it automatically saves your residuals. It automatically saves your residuals. So what we're going to do, this tells you all of the directions right here. It says the TI-84 generates the residuals when you perform a LINREG. They're stored in a list called Residual ID. That's what this stands for, Res ID, Residual ID. And it's found in the list menu. So we want to go in and create a plot. So we're going to go back. First of all, I'm going to go in and I'm going to erase my y equals line. I'm going to go back into stat plot. My stat plot's on. I want to click that. And this tells you my X value comes from line 1, my Y value comes from line 2. Now, if you look at this graph, miles driven is the same on both of these graphs. It's my Y-axis that changed. My price is what changed, and this became the residuals. All right, which is still, my unit is still dollars, because it's the dollars above or the dollars below our predicted value. So from our calculator, you're going to go in here, and you don't want the Y2 data anymore. This is where you want your residual data. So to do this, you're going to do a second stat, which gives you a list. Yeah, second stat tells you that right here in the directions. And you're going to go down and you're going to pick residual ID. And now I see it here, and now I can go ahead and graph that. Oh, I'm going to do zoom so we see it better. There we go. So there's my zoom stat. And so this residual ID, or this residual plot, is this same residual plot that we have up here, because all the data is the same. This way you're just copying it down so that you have the same data. Okay. Let's see, what else do we want to do here? Oh, bad residual plots. You don't have to draw this, but I do want to talk to you about bad residual plots. So what I have when I have this residual plot is I'm going to have data that's above and below this residual plot. So what we want in a residual plot is complete randomness. We want dots above, we want dots below, we want it to be completely random. If it's completely random, then we don't have a pattern. There are two types of residuals that are going to show up, and if you get these types of residuals, you know there's a problem in the data. And so if there's a problem in the data, then this means it is not linear. So one example of this is a residual plot is if residual is if it looked like a parabola. So if you have data that looks like this, that would be a bad residual. And so we know that our least square line, the line that we created, is not a linear line, right? So if you remember, when we're looking at scatter plots, we could have a scatter plot that's linear, we could have one that's exponential, we could have logarithmic, we could have quadratic. If we see a pattern here, then we know that we don't have a linear function. And so what this means is that your least square regression line can't be a linreg. You have to run some other regression. Another option, they call it this Christmas tree pattern, is if you have something that looks like this. And you have data that falls in here. But the data looks like a Christmas tree. If you see this, it's almost like a sideways absolute value graph. So this would be another example of non-linear. You should not have run a linear linreg. That's what that means. So if you think back on where we were a couple of days ago when we had the graph where I said, you know, it could be linear, but it could be logarithmic, you have to look at your residual plot. If your residual plot gave a pattern that looked like a parabola or a pattern that looked like a Christmas tree, then you know that you can't run linreg and you have to go back and run the logarithmic graph, the logarithmic regression. Okay? All right, so this is only the first part of section C, residuals and creating our coefficient of determination, so our R squared value from R. So I'm going to create another video for the rest of this unit, which is creating our least squares regression lines, these lines, creating these by hand. Okay? That'll be the second video for C.